Hey everyone, this is Geek37 back with another video, and this is part 5 in the Exploring the Heptagonal Triangle series. But as you can see, I have the regular heptagon on the whiteboard here, and the reason why is because I want to demonstrate the sine and cosine ratios that would go with the heptagonal triangle, but the best way to show that is with the regular heptagon. So like I said, sometimes we have to go to the whole shape in order to understand the smaller pieces. So what I'm going to start off with is I'm going to connect the diagonal from point F over to point D here, and I'm going to drop a perpendicular from E right down to here. Now, here's what we need to understand. The angle on the outside of the regular heptagon is 5 pi over 7. And the reason why that is because when you set up the regular heptagon, like so here, pardon my bad drawing, and you were to draw in the triangles like you did when you were in, say, middle school learning this for the first time, you'll notice that there's 5 triangles here. So 5 times 180, well, that's 5 pi. So that's where that comes from. And each angle on the outside has to be 7 because you take 5 pi divided by 7. So if the angle up at the top here is 5 pi over 7, and we have the sides here being the same because these are side lengths, and in fact, we've been using the letter A to represent the side length, as you know from me drawing in the heptagonal triangle. Let's just draw that in quickly for reference down below here. We have A as the side length, B is the short diagonal, and C is the long diagonal, and this is pi over 7. This is 2 pi over 7, and this is 4 pi over 7 right there. Well, let's go up to the top here. We have this triangle EFD, and we have two sides being congruent. That means this triangle is isosceles, and we know for a fact that that measurement is pi. So if we take pi minus 5 pi over 7, we'll get 7 pi over 7 minus 5 pi over 7, and that will get us 2 pi over 7. Well, that's the thing. We have to take 2 pi over 7 and cut it in half. So the angle in each corner here is pi over 7. Well, the thing is, the entire length of D to F is B. But the thing is, we also have the length of from the center here over to the vertex. Well, that has to be half because we're dropping the altitude from the vertex of this triangle, EFD, down to the center point. So that is B over 2. So if we looked at the sides here, we got this B over 2. We have this A, and we'll notice that the angle here, pi over 7, well, B over 2 is adjacent, and A is the hypotenuse. So the cosine of pi over 7 is B over 2A. And if you look at the article, if you look at the article in Wikipedia for the heptagonal triangle, you'll see that the cosine of pi over 7 is B over 2A. Let's go on to the next angle, which is 2 pi over 7. So now what I want to do is we'll change over to a different color, and this time I'm going to connect E to G, G to C, and E to C like so here. And as you can see, we're skipping one vertex. So this is the short diagonals of B and B, and this right here is the long diagonal of C. Now let's figure out the angles or the angle measurements inside this isosceles triangle. Before we do that, let's drop down the altitude like so here. So let's figure this out. We know for a fact that we have this triangle right here, GFE, and this isn't one of the isosceles triangle. That's the isosceles triangle from before. So the angle up here is pi over 7, and the same is true on this side over here. Let's label these with A's. So these triangles AAB, again, A is the side length, B is the short diagonal. We found that each of those smaller angles was pi over 7, but we know that the vertex angle is an angle, the vertex angle on the heptagon itself is 5 pi over 7. So inside here, let's mark this with a highlighter. So we're showing this entire arc right there. That entire arc is 3 pi over 7. Well, the thing is of course, every isosceles triangle, every triangle has pi radians on the inside. It doesn't matter if it's scalene or isosceles or equilateral. What we're going to do is we're going to take pi minus that vertex angle of the triangle, 3 pi over 7. Well, again, we get 7 pi over 7 minus 3 pi over 7, and we get 4 pi over 7. But we have to cut that in half, so that's 2 pi over 7, which of course is 1/2 times 4 pi over 7. Show the cancellation. That's 2. So that's where that comes from. So each vertex of that isosceles triangle has an angle measurement of, or excuse me, the base angles of that isosceles triangle have measurement of 2 pi over 7. Now let's do the same thing we showed earlier. I'm going to mark in highlighter here. Let's do this pink one. This length here and this length here, because we're establishing a cosine relationship like I did in the last part of this video. What happens is we're taking that part, and the distance from here to that vertex at G is going to be C over 2. So the cosine of 2 pi over 7 is going to be C over 2b, because C over 2 is the adjacent side and B is the hypotenuse. So that will set up that one for us there. Okay, now we have to do the next one, 4 pi over 7. All right, everyone, now let's get to the central isosceles triangle in the regular heptagon. We're going to draw diagonals from E to A and E to B. And as you can see, we're skipping 2 vertices on each side, so this is the long diagonal, so both of those get labeled C. And of course, AB at the bottom is a side length, so this is A. So if we drop the altitude down from the top, we will see that down below here, this will be A over 2. And we'll be able to set up the cosine relationship from there. But the question is, what is the angle at vertex A and vertex B and the angle at vertex E? Well, here's how we figure that out. This time is a little bit more, this one's here is a little bit more difficult. Now, the thing is, and I've not actually proven this, but this is a fact about side lengths and their diagonals. There are diagonals that are actually parallel on the inside to the side lengths. And as you can see from where I drew DC here, A is parallel, or segment DC or side A here is parallel to EB here. And as you can see, we're forming what's called an isosceles trapezoid because of these sides being A. Well, the thing is, since D and C are vertex angles on the side, those are 5 pi over 7. And because we have parallel sides here, what happens is this side that I'm overlaying in green, where angle D is, and we're right up here where vertex E is, this forms what's called a same side interior relationship. So the same side interior angles are complementary. So if we take pi minus, or not complementary, they're supplementary, I'm sorry. I should know that, I'm a former high school math teacher. So we take pi minus 5 pi over 7, 7 pi over 7 minus 5 pi over 7 equals 2 pi over 7. So the angle measurement here is 2 pi over 7 for both of these. Okay, well, that begs the question. Let's say down here at the corner we have the 2 pi over 7, and on the outside, because of the vertex, we have 5 pi over 7. Well, what's the angle measurement on the inside here? Well, that's 3 pi over 7, because 5 minus 2 is 3. And because of the nature of isosceles triangles, the altitude is a line of symmetry. So on the other side, this must be 3 pi over 7. And up here at the very top angle here, 3 pi over 7 plus 3 pi over 7, well, that equals 6 pi over 7. So that means pi minus 6 pi over 7, well, that'll equal pi over 7, which is our vertex angle right there. Now, again, we're establishing a cosine relationship in this very triangle. So what happens is we're going to do a over 2 as the adjacent side and c as the vertex. So therefore, the cosine relationship for 3 pi, oops, my bad. The cosine relationship for 3 pi over 7 is equal to a over 2c. But remember, the triangle, the heptagonal triangle, has pi over 7, 2 pi over 7, and 4 pi over 7 as the angle measurements there. The question is, how do we get 4 pi over 7 from 3 pi over 7? Well, the thing is, there is a trig identity, a very well-known trig identity that says the cosine of pi minus alpha, let's say alpha is any general angle, is equal to the negative cosine of alpha. So let's do the quick math here. Pi minus 3 pi over 7, which of course equals cosine of 4 pi over 7, is going to be the equivalent of the negative of cosine of 3 pi over 7. So let's put that box here. So down below in this box, we're going to put the cosine of 4 pi over 7 will be the negative of that fraction above. And that ratio is shown in the Wikipedia article for the trig ratios of the heptagonal triangle. All right, now that we have established the cosine ratios, what I want to do next is establish sine ratios for sine of pi over 7, 2 pi over 7, and 4 pi over 7. So to establish sine ratios, we have to deal with the circumradius, which comes off the very center of this polygon. So what I'm going to do to start this off is I'm going to take the circumradius r here, and I'm going to extend it from the center. And typically the circumcenter is labeled O, dealing with triangles especially. And what happens is we'll drop a perpendicular like before going down, and as you can see, we're forming an isosceles triangle like we did in the last several examples that I showed. And we will we'll label AB here as, of course, A, and we have R here. And the thing is, what is the angle measurement of AOB? Well, the thing is, because of every regular polygon being able to have a circle drawn around it, you can easily figure out what the measurement in the center is by taking 2 pi, which is equivalent to 360 degrees. So every triangle has 360 degrees in it coming off the center, and then we can divide that by 7. So the angle measurement here, which I will swoop in with this pink highlighter, is 2 pi over 7. So cutting it in half here, this makes it pi over 7. And down here, if we were to label this part here and do this, well, we are establishing a sine relationship, so it's opposite over hypotenuse. The length here that I've labeled from the point where the altitude meets the side length over, that's that is A over 2. So then the sine of pi over 7 is A over 2r. So our sine ratios are going to have the diagonal or the side length over 2r, and that's what I'm going to establish in the next two cases. So now that we've established uh, sine of pi over 7, let's establish the sine of 2 pi over 7. And what's going to happen is we're going to connect from, we'll label that, again, we'll label the circumcenter as O. We'll go O to C and O to A. Now this time what we're going to do is we're going to connect A to C. So we have B here. And what I'm going to do is I'm going to drop down the altitude here of this triangle. So what happens is we have the center this time. Since we're skipping 2 vertices, this time the angle at the top here is twice 2. This time it's twice 2 pi over 7, thus making it 4 pi over 7. So the angle right here, AO, I'm going to call this M for midpoint because it's the midpoint of that diagonal. It's going to be B over 2 and the length here of R. So the sine of 2 pi over 7 is going to be B over 2R, just like that. All right. Now we have one more, or excuse me, 1.5 more of these ratios to establish. So to finish this particular video, what I want to do is I'm going to connect G to C this time, and we'll connect O to G and O to C. Now, as you can see this time, you're skipping from C to B to A to G. If we were to draw these in right here, we know that each of these corners here is 2 pi over 7. Well, of course, 2 plus 2 plus 2 is 6. So this angle at the top here is 6 pi over 7. Now, with that established, there we go. We'll drop the oops. We'll drop the vertex down to here, call M. In this particular case, that's our new midpoint. GM is going to have a length of C over 2 because the entire length here from G to C is C because we're skipping 2 vertices. And of course, the length coming off of O here, O to G and O to C will have the length of R because those are circumradii. The thing is, we have 6 pi over 7. We have 6 pi over 7 as the vertex here, so half of that would be, so 6 pi over 7 times 1/2 is equal to 3 pi over 7. So the sine of 3 pi over 7 is equal to C over 2R. But again, the vertices in our heptagonal triangle, let me just quickly draw that for reference here, are pi over 7, 2 pi over 7, and 4 pi over 7. So A, B, and C. But the thing is, the nice thing about the sine of pi minus alpha, it's equal to the sine of alpha because of the way that sine is between 0 and 180. They're all positive. So if we take the sine of pi minus 3 pi over 7, we get the sine of 4 pi over 7. So the sign remains positive. So as I draw in this second box here, the sine of 4 pi over 7 is equal to C over 2R. So all those sine ratios are positive. Okay, so I hope that makes sense on where the trig ratios for the heptagonal triangle come from for all 3 angles. I needed to use the regular heptagon as a whole to establish these. I figured showing the isosceles triangles for the cosine cases and the sine cases would be the easiest way for people to understand that. And like I said, Sometimes you need the whole shape to understand just the parts of it. And as you could probably see from the Wikipedia article, they don't show any of that understanding, which is why I decided to make this video. All right, I hope you enjoyed this video. I enjoyed making it. This is Geek 37 signing off.